Hello and welcome back to Abstract Linear Algebra, the video course where we talk about general vector spaces and general inner products. And there we find an important notion given by so-called orthonormal bases. Therefore, in today's part 18, we will explain what an orthonormal system is and what an orthonormal basis is. However, before we start with the definitions, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please use the link in the description to download additional material. Okay, then let's immediately start by stating the general assumption we have for this video. In fact, it's the same as in the last video, namely we have a general F vector space V with an inner product and a subspace which is finite dimensional. This means we can write down a basis for U with k elements. And now the general idea is that we choose the vectors in such a way that we get a nice basis out. Now, this could mean anything, but since we have an inner product here, we already know what nice could mean. Since we can measure angles, we could claim that the angle between two basis vectors is a right one. So we want orthogonality for the basis vectors. And we already know this one we can put into a nice formula. In particular, if we have B1 and B2 here, we would write that the inner product with B1 and B2 is 0. So not so complicated, this is exactly what we mean by orthogonality. On the other hand, we can also just put B1 into the inner product and then we also get out a number. In fact, we already know this number represents the length of B1 squared. Obviously, this should not be 0 because we don't want the 0 vector for the basis elements. However, it could be any other number and therefore it would be nice to choose a good number again. And a good number for us would be 1. You see, this is already a good choice because 1 will not change after doing the square root here. And of course, we want the same thing for the second basis vector, B2. And actually, we want to have it for all the basis vectors, and also this first equation we want to have for all possible combinations. And to put this claim into a formula, we have a very helpful notation. We just take indices I and j that go from 1 to k, and then we say that this resulting inner product is equal to the Kronecker delta. And if you don't know the Kronecker delta, it's no problem at all, because it's a really simple symbol. It just distinguishes two cases, namely we have 1 or 0. And now you might already know, the first case we have if the indices coincide, and the second case we have if they are actually different. Okay, so there you see, this is the formula we want to have for a nice basis. And of course it will get a special name later, but now you could ask, why is this basis beneficial at all? This is something we should immediately answer, and we can do that by checking out the orthogonal projection again. Please recall, we could calculate this orthogonal projection for any vector x in V. This means any such x can be decomposed into two parts. The first part, xu, is an element in the subspace U, and the second part is perpendicular to this. Therefore, we call xu the orthogonal projection of x onto u, and the other part the normal component. And we've already seen it's nice to have such a decomposition, but it might be some work to calculate it. In fact, in order to calculate it, we need the so-called Gramian matrix. And we write G of B because the Gramian matrix is always related to a chosen basis of U. So there you see, the choice of a basis comes into the calculation. Indeed, we also have it on the right hand side here because we calculate inner products with the basis elements and x. However, the whole thing is not a big problem because just inverting the Gramian matrix solves the whole system. Or more efficiently, we can bring the system into row echelon form and find the unique solution. Therefore, this whole procedure is very quick if the Gramian matrix is in a nice form. And there you see, now the nice basis from the beginning comes in. So we just have to recall how the Gramian matrix was defined. And in fact, the only things that go into the Gramian matrix are the basis vectors of U. And since everything inside is given by inner products, a condition like the one with the Kronecker delta before really helps. Because it immediately implies that the Gramian matrix is just the identity matrix. Indeed, you should see we have zeros everywhere except on the diagonal, and there we find ones. And then you should recognize that the whole LES here is super easy to solve. In fact, the scalars we search for are immediately given by the right-hand side. Hence, we can directly write down the orthogonal projection XU. We have the scalars, so we know the linear combination. So we have a sum that goes from j is equal to 1 to k. Indeed, the scalar we already know, it's bj with x in the inner product. And this is the scalar for the basis vector bj. So this is the linear combination we need, and it gives us the orthogonal projection of x onto u. And it turns out the whole thing is easier to remember if we put the vector in front and the scalar to the end. Because then you can just remember that an orthogonal projection is given by such a combination of bj with bj. However, it only holds for such a nice basis, and now we will call it an orthonormal basis. Therefore, this will be the content of the next definition. It's a very general definition because we only need a vector space with an inner product. However, still, because we do linear algebra, I want to formulate everything for a finite dimensional subspace. One can generalize that for infinite dimensional subspaces, but this is a content for another video. So here we just take a family of vectors from the subspace U, and as before, let's simply call them bj again. And then we have different names for this family depending what it fulfills. The first notion is just orthogonal system, in short OS. And as the name suggests, there we just need that the inner product vanishes. So we don't claim for the Kronecker delta here, we just claim for 0 in the case that I and j are not equal. So no matter how we put two different vectors together, we always get out 0. So this simply means that the vectors are mutually orthogonal. So if we combine two different vectors, we always find the right angle there. Sometimes this is already helpful, so the length is not important for the vectors, but you already know we want more. Hence, the next thing here is an orthonormal system, in short ONS. And there, in addition to the orthogonality from before, we also want to set the length of each vector to 1. And you already know, for this we can use the Kronecker delta. Now, at this point you might realize that we didn't say anything about a basis yet, and the reason for that is that these two cases are more general. In fact, they can also make sense if we change the number of elements in the family. So for basis we need exactly k vectors, but for an orthonormal system we could have less vectors. And this already explains why we get two additional names. Namely, we get orthogonal basis OB and orthonormal basis ONB. So we have exactly the same thing as before, we just add the information that we have a basis as well. And then we get the most important notion, namely orthonormal basis for a subspace U. Now, this notion should not be completely new to you, because you already know Rn with the standard inner product. And of course, this is the standard example we should mention here. And maybe let's keep it at 3 dimensions, because then it's easier to write down. There you also know the standard basis, the canonical unit vectors form a basis. And now it should not be a surprise for you, with respect to the standard inner product, this is an ONB of R3. And you might remember, in R3 it's easy to calculate with this basis because it's an ONB. And this also translates to more abstract examples, so we can see that we always want to have an orthonormal basis if possible. Hence, the question arises, can we transform any basis into an ONB? And indeed, the answer is yes, there is a procedure for that, and we will talk about this in the next video. So I really hope we meet there again, and have a nice day. Bye bye.